Hello everyone, welcome back. I hope you have seen this previous video on heap, the part 1. If not, I would highly recommend and suggest that please go through the part 1 video so that you can better understand what has been explained in that. That includes the point number 1, representations, and what is meant by Heapify. Okay, and after that, what we are going to cover today is the priority queue. We are going very slowly so that students can understand everything right from the basics before moving forward. Okay, so if you have not watched that video, please go ahead and watch it. Otherwise, let's quickly move to today's video. Awesome. So today we are going to learn about priority queue. Okay, so first let's understand what is meant by priority queue, and then we will be learning about why we need this data structure, what is its importance, and it is very important from your exams or maybe from interview perspective because a lot of questions are asked on it. Okay, so first we will understand what is a priority queue. So it has two words, priority and queue, right? So let's first understand what is a queue if you have not known about it. So a queue is a data structure that has a front and back, and the property is that things or any element or data will always be inserted from back and taken out from front. It is not possible that you can access any element from this area. It is not allowed. You can only access an element from the front. There are few queues, double-ended queue that is called deck, or maybe few implementations can provide that okay, you can access from back as well, but ideally and the classical queue does not support that. Okay, it is not allowed. So that's why you will always see that in a queue you will have functions like push, which will always push from the back. It has some say data. And you will have pop that will give you the data from the front. So that is the property of a queue. Now when you say a priority queue, that means you will always get the data out from front based on some priority. You can decide the priority. Let's say for us the priority is the number. If it is higher, then it is having more priority. It is lower, then it is having less priority, right? So when you say from a priority queue, let's say you have a priority queue represented by some say object PQ dot front, or let's say dot pop, it is guaranteed always give highest priority element. Okay, so that is the property of a priority queue. Now why we use heap in it? If you remember, and I go back to the representation of heap, when I said max heap, you can see here that the root here, if I can change the color of the pen, the root here at this point, it is having the highest priority. That's why it is called the max heap. Okay, that means we can very effectively use our heap data structure for creating our queue. If we remove 17, then whatever be the highest priority or number in the heap will take its place. In this case, it will be 14. Or if we add some another number, then and if it is more than 14, then it will take its place, right? So that means we can very effectively use heap for this purpose. Okay, some of you who know more about data structures can argue that why not use sorting, because if you sort in descending order, then you will always get the highest number or highest priority right from the top. I agree with it, but still there are cases where the implementation of a priority queue based on heap will be faster in few cases than the sorting based approach, and that I will going to cover later in today's lecture. Okay, so till now we have understood that for a priority queue we can very effectively use our max heap algorithm. So let's see how we can create our priority queue. Okay, so let's understand with an example how we are going to create the priority queue. Okay, so I am taking the example of any 5 elements: 3, 8, 5, 1, 9, and I'm drawing a margin here so that at the left right hand side I will keep on drawing how it will be inserted in a queue. You can assume this is the back and this is the front, and on the left hand side I will be having the tree structure. So this is 0, 1, 2, 3, 4. First of all, we start from 0th element. We get 3. We will put it into the tree. This is the only element. We will put it into the queue. So this element has the highest priority because it is the only one. So we can move forward. Then we get 8. So we will insert 8 here and insert 8 here. We can clearly see it has violated our max heap property. So what we will do, as we did yesterday, we are going to swap these. We will say 8 will become here and 3 will become here. And similarly, we are going to swap these nodes as well. Okay, remember, for the array representations, we are going to find the parent and child using the formula in previous video. Then 3 is done, 8 is done. Next is 5. So we will insert 5 here and 5 here. At this moment, 8 is having the highest priority and it is at our top, at our front, at our root. So our heap is following that property perfectly. Next, move to next element, which is 1. We will insert 1 here and we will insert 1 here. So as we can see, this is again perfectly following the property of max heap. Awesome. Don't get confused that 3 is ahead of 5. No. See at the left hand side. See at the left hand side. I would mark with a different color here. So this one is very clearly following the property of max heap. As I told in the previous video, it doesn't matter whether the left child should be greater or right child. That happens in binary search tree. In case of heap, you only compare with the parent. The comparison of children is not done, is not required in case of heap. Awesome. So we are done with, if we can change back the color. We are done with 1. Let's move to 9. 9 will be inserted here and inserted here. Now you can see the property is violated. Okay. So what we will do is, we will do a Heapify. Now is the time to do Heapify. Let's do it. So where the property is violated, where we have inserted it. So we can see that 3 is less than 9. So we will swap those. So we will quickly swap 9 with 3. Great, but okay, we have to do at the right hand side as well. So let's do that. 9 and 3. 9 and 3. But we see after swapping that, again 9 is still smaller than its parent. So we have to move up the ladder. So what we are going to do, we are going to swap 9 and 8 as well. And at the array side also, we are going to perform the same. Now it is following the property of max heap. This is our priority queue at the moment. Right? So if you see what we have done, we moved from here until here. That means this is a very important point, and that is why this structure, this data structure is so important, because a Heapify operation at max takes log to the base 2 n time, okay, which is equal to height of the tree. In case you use sorting, then you have to traverse the entire length of the array, and its complexity will come out to be, it's big O of notation, big O of n. Because you have to shift entire array sequence to maintain the sorting order. Here, we are just concerned about the highest priority element, right? And that is why we are able to perform it in height of the tree, which is log to the base 2n, which is much better in terms of time complexity than the linear one. And if you want to perform the removal of element, let's see how that happens from the priority queue. So this part I remove. Great. Now let's remove the elements from the queue. So as I told, you can always remove from the front. So what you will do, you have to remove 9. So when you say I want the highest element, I would say front. It will return me 9. Okay, but that's fine. But when you remove that, you have to make sure that your property is maintained. So who will take space for 9? We don't know. Okay, we are going to do it, and let's see how. In this, at the left hand side, what we have to do, we have to swap the root with the last element. Okay, and when you swap that, what you will get is 3 at the top and 9 at the bottom. And this is done once you have returned that the answer is 9, okay, because now we are changing the data structure internally. And in our array also, we have to do that. We have to replace three with 9. And because we have taken out 9 from the queue, we no longer need it inside our queue. So we will not put it. We will just discard it. So you can see our queue has become smaller, but the property of heap is not maintained. Max heap. Since we have changed the root, so we will check whether it is following the property of heap or not. Is 3 greater than both the children? No. So there are 2 candidates as of now, right? One candidate is 8 and one is 5. Which one will you use to make the root? Obviously, which one is greater? Either the left one or the right one. So what we will do is, we will take the higher one and swap it. So what we are going to do, we are going to swap 8 with 3. At the right hand side also, we are going to swap 8 with 3. Is this following our property? Exactly. So we are good, because 3 is again greater than 1. This sub heap is also following the same property. Okay, so after this done front, we would have done pop. That's why it is removed. And now again you do a front. You will get 8. And again you do a pop. So now 8 will be removed. So what we will do again, same thing. We will swap the 8 with the last element. Okay, and we will discard the last element. Right? But again, the property of max heap is violated. So what we will do, we will check whether it is following. It is not. So which one is greater? This time the element at the right side is greater. So we will replace it with 5 here and 1 here, and similarly 5 here and 1 here. Now we are again back to heap. Okay, and if you want, you can continue this in the same manner. So this is about the priority queue, and what we have learned is that why it is important, because you will be able to insert or remove element in log to the base 2 n time, which is greater than the sorting algorithm time of n. That is why when you just want the highest priority element, we prefer a priority queue data structure over sorting. Because in sorting, you have to do it in n time. Okay. So with this, I think that's all for today's lecture. I'll see you again in next video, where we will be moving towards the heap sort. Okay, again, thanks for watching. If you have any questions, please put down in the comments below. See you again. Thank you. Bye-bye.